Mhm. Okay, I'm going to go live now. Give us a moment to. Okay, hi everyone. Welcome to the Topos Institute Colloquium. Today we're very honored and pleased to have Simona Paoli, who's going to be sharing with us about simplicial delta versus fat delta in higher category theory. Thank you, Simona. Whenever you're ready.
So thank you very much. I'm really delighted about this invitation. I heard a lot about the Topos Institute, and I have a lot of admiration for this this initiative. So I'm really happy to be here. I know that a lot of your focus is in applied category theory. I cannot say that this talk is about applied category theory, but I know that you're very receptive to the ideas or kind of more foundational work. And since the things that I'm going to present, I think, are quite new, I hope that this could interest you, and possibly maybe some of you at some point might bring these things inside the kind of applied world. I have written a lot of slides. I'm not really planning to go through all of them. I would like to mostly concentrate on the main ideas and concepts, but I put things there in case some of you want to go over these things later. And this talk is about different types of combinatorics that people have been using to talk about higher categories. Although I will stick to dimension 2, but my sort of long-term goal is to do this in dimension n. Let's start with a very familiar combinatorics, the one of the simplicial delta, which I remind you is the category whose objects are finite ordered set. So, sorry, I have a little bit. So n is sequence of 0 up to n ordered, and the morphisms are the non-decreasing monotone functions. So this is a nice category, and it embeds a combinatorics that we call simplicial object. So a simplicial object is the functor category from delta up to set. A simplicial object can also be presented as a sequence of objects. Here, xn is x at the ordinal n. And these are connected by so-called face maps, one pointing towards the right and the degeneracy map pointing towards the left, subject to the simplicial identities. As you know, these things arose really in topology because simplicial sets is a model of spaces. That's a famous result of Duncan. So why do we talk about simplicial objects in category theory? What do these things have to do with categories? Well, there is a fairly elementary way to understand this through something that is easily associated to a simplicial object, which are the so-called Segal maps. If you have any simplicial object in a category C with pullbacks, then you can construct the following commuting diagram. And if you look at the limit of the bottom part of this diagram, which is this iterated pullback, then there is a unique map from xk to this limit. So why does this have to do with categories? Because if you have an internal category in C, which is nothing else than like a category, but where all the objects and arrows and maps live inside your context C, then there is a so-called nerve functor from internal categories in C to simplicial object in C, which is built exactly as you do for the case of C equals set. So you have at level 0 the object of objects, then the object of arrows, then the object of composable arrows, then the object of the string of arrows of in general length n, and the phase operators are given by the composition, the projection, and the degeneracy are the insertion of the identity arrows. So here is a fundamental fact, which I think was first observed by Grothendieck, which is that a simplicial object in C is the nerve of an internal category in C if and only if the Segal maps are isomorphism. So this was really a very fundamental thing to get people started in using simplicial combinatorics to do categories, but in general also higher categories. And one sort of entry point into this is the fact, which is also quite elementary, that the internal category construction can be sort of repeated. So if you start with C equals cat, you can do, for example, internal categories in categories. These are well known. They're called double categories. Throughout this talk, for me, double categories means strict double categories, so internal categories in cat, because in some other parts of the literature, double categories means also pseudo double categories. That's not what I'm doing here. So in elementary terms, you can think of double categories as having objects, more vertical morphism, horizontal morphism, squares, and then you have X0 is a category. So these morphisms, this vertical morphism can be composed vertically. So correspondingly, you can vertically compose your squares, and you can also horizontally compose everything. Okay. So this structure of double categories, although it's that easy to define, is far from being trivial. I think we have already quite a few experts in the audience, more experts than me, that have done a lot of nice work on double categories. It encodes a lot of complexity. In fact, I would say that in this level of generality, maybe not everything is yet understood about even strict double categories. We could specialize to the case where you double categories is such that all these vertical morphisms are identities. Then you can take one of these squares and squeeze the vertical arrow. So what do you get? You get a globe. And what is this? It's a strict two category. So you can say that if you want to describe strict two categories simplicially, a strict two category is a simplicial object in cat, such that all the Segal maps are isomorphic, but X0 is a discrete category. This is just another way to say that you have a category enriched in cat. But I really want to concentrate on this particular description, because as I'm going to illustrate, then there will be something formally similar to this description, except that instead of the simplicial delta, we're going to use the fat delta. Now, some years ago, Joachim Kock and myself came up with a structure which is somewhat intermediate between these two things. It is a double category, but not a general double category. And it is something more general than a strict two category. So this X0 is not a discrete category. And the idea is that you replace discreteness with something close to discreteness. What is a category very close to a discrete category? Well, it's a category equivalent to a discrete category. That is necessarily a groupoid, a very special type of groupoid, because it's a groupoid where you cannot have non-trivial loops. Yeah. So topologically, it's a zero type. So it's just a fattening of a discrete thing. And that's what gives us the category of weakly globular double categories. So you have simplicial object in cat such that all the Segal maps are isomorphic, so that we have a double category. We have this weak globularity condition. So X0 is an equivalence relation. So necessarily it's a category which is equivalent to the discrete category on its set of connected components. And you have this map from X0 to X0D. And we also called such a category homotopically discrete. But that is not all. So basically, this is a structure in which we want to think about this set of connected components as being the set of objects in your higher structure. But then let's look at a picture like this. You see, if you had horizontal arrows whose source and target don't match up precisely, but they live in the same vertical connected component, you would like to somehow be able to compose this staircase. Yeah. So you need a condition that allows you to do this. For example, the condition that says such a staircase could be lifted to a sequence of truly composable arrows in the double category, because the staircase is not composable in the double categories, but if you can lift, then you have a composition there. So this third condition is what allows you to exactly do that. Formally, it says this map, which is induced by the map gamma from X0 to X0D, so we call it the induced Segal map, is an equivalence of categories. So this is the definition of weakly globular double categories. And why did we want this? Because we were looking at a way to describe weak two categories, but using strict double categories, which may sound surprising at first, because how can a rigid structure as a strict double category actually encode the weakness and all the coherences in them? But it turns out that this is exactly what happens. So this weak globularity, together with this condition, is, if you like, a new paradigm to weaken a strict category into something weak. And the main result that Pronk and myself proved is that this cat2 weakly globular is suitably too equivalent to bicategories. Maybe I'll spare you the sort of technicalities. Well, I cannot possibly go into the technical details. In the previous slide, I spelled out that there is a notion of two equivalents in cat2 weakly globular, which mimics exactly the biequivalences of bicategories. But perhaps I will skip this for the moment. There is actually a generalization of this to high dimension, which is what I did in my book. So there is a category of cat-n weakly globular, which is a model of weakened categories because it does satisfy the homotopia hypothesis. But this was the basic case that was very important to get started. And so this is one use of simplicial techniques to describe models of weak two categories. And now I'm going to tell you about a different combinatorics, which is the one with the fat delta. And as far as I can tell, not many people have worked on it. So fat delta was introduced by Joachim Kock, I think, back in 2007. I don't think I'm the only person that has been interested in it, but not that many. And I think this is a big shame, because it's, in my view, a very, very interesting category, as I am finding out. And so part of the goal of my talk is to also, gain some interest in this, because I think it would be useful even besides the specific things that I'm going to tell you about. So let's first come to the definition of fat delta. The definition I'm going to give is the less intuitive definition, which is not the one that was originally given by Kock, except that this definition is the one that is most useful to actually give the proofs and really get things done. So we start from the category of epimorphism in delta. So the objects are the epimorphism in delta, and the morphisms are the commuting squares like this. In the fat delta, the objects are still the epimorphism in delta, but the squares that you consider are the ones in which the top arrow is a monomorphism in delta. Okay. Now, presented in this way, this looks completely mysterious. What is this thing? How far it is or close it is to the simplicial delta? So here is where we want to use the sort of more intuitive approach of Kock, and let's start first with the epimorphism in delta. How can we think about it? So remember that an object of delta can be considered as a category, the ordinal n. And remember that if you have a category, there is a notion of wide subcategory. What is that? It's just a subcategory with the same set of objects. Now, suppose you have an epimorphism in delta. Yeah. So this identifies a wide subcategory of the source, so n prime, by saying if you have I less than or equal to j less than n prime, then you have a morphism from I to j if eta of I is equal to eta of j. So these are the morphisms of your wide subcategory. So let's look at this example, right? So you have this epimorphism from 2 to 1, and you have a wide subcategory in which the non-identity morphism is the morphism from 0 to 1, because these are the two things that are mapped to the same 0 by eta. So the way we can think about this is in terms of so-called colored categories, which I think is the same concept as relative categories. I'm using the terminology colored for consistency with Kock paper, but it's the same notion. So you think of this as a colored ordinal in which the colored arrow in this case is exactly this arrow depicted as a link. And now what about a morphism in AP delta? What is that? Well, let's look. So here you have this commuting square, right? So you have a colored ordinal n prime, a colored ordinal m prime, and you see that the commutativity of this square is exactly saying that colored arrows are sent to colored arrows. Yeah, it's clear because omega 1 of I, not omega, sorry, eta 1 of I equal eta 1 of j implies eta 2 of f of I equals eta 2 of f of j by the commutativity. So what's the upshot of all this? Epimorphism in delta is isomorphic to the category whose objects are the non-empty colored ordinals and whose morphisms are the color-preserving functors between them. And with this description, you can start seeing now there's a much closer relationship, at least intuitively, between this fat delta and the ordinary delta. But wait a minute, because this is not the fat delta yet, right? So what does this monomorphism at the top is doing? So far, I've been giving you a more intuitive description of this. What about the fat delta? So to explain this, we need to remind the notion of semi-category. A semi-category is like a category without identities. And remember that inside delta, we can consider the wide subcategory with the same objects and map up the monomorphism. So we denote it by delta mono. Delta mono is isomorphic to the category of finite, not empty semi-ordinals, right? So we can identify semi-category with functors from delta mono up into set. These are also sometimes called semi-simplicial objects. So the nerve of a semi-category is a semi-simplicial object. There are only phase maps, no degeneracies. And so having that monomorphism at the top means that we can think of the fat delta as the category of finite, non-empty, colored semi-ordinal and color-preserving maps. Okay, so at the level of the pictures, you can sort of picture things in the same way, but you have only semi-ordinals around here. Another thing that I want to say is that we have this map pi from the fat delta to the ordinary delta, which is just taking the surjection here at the target. And this is quite an important map. All right, so what do we do with this? First of all, one slight other thing that I want to say, there are two embeddings of delta mol into the fat delta. One is to say, if you have an ordinal here, you can take the surjection consisting of the identity, or you can take the surjection consisting of the map going into 0. This means in the first case is basically just the ordinal with nothing colored. In the second case, everything is colored, okay? And you have the maps in the obvious way. And very often we just omit H. When we talk about H, we just don't write it. So we say H of n is equal to n, but V instead, we want to have it there because it means you're coloring these links. Now, one of the nice things about this fat delta is that it supports a combinatorics of Segal maps, which is formally very similar to the one of the simplicial delta. Again, I would just like to give you an example rather than all the technicalities. Let's look at this example, right? You have this epimorphism from 6 to 3. And it means that you put links when things coincide in the target. So you put a link between 0, 1, 1, and 2, and between 5 and 6. So suppose you have now a functor from fat delta up into C. Then you have a Segal map from X. Now it will be indexed by this eta. And on the right-hand side, you have a pullback, which is formally similar to the one that we had for the delta, except that whenever you have a colored link, you have X of V of 1. Whenever you have a non-colored link, you have X1. So you have two colored links here, and you have two copies of XV of 1, three things that are not colored, and you have three copies of X1, and then a final XV of 1. the formal proof of this is basically very, very similar to the simplicial data. You write down these commuting diagrams from which you extract these Segal maps. And, the formalization is to say, given a surjection like this, you can characterize, these links by being the pre-image of the things for which the pre-image has a size bigger than 1, and then you give some numbers, keeping track of the length of these links, of the length of the stuff that is not linked, and you write down in a general way the general form of the Segal map. And I've done it in the previous slide, but I don't think it's worth, going through these technicalities, because you see from this example how this is generalized. So, look, we have the category of fed delta up into C. We have a notion of Segal map. So why don't we mimic what we did to define strict two categories simplicially? Well, basically that's what Kock did when he introduced the notion of fair two categories. But there is a small catch, because now you have these colors around. So you are working with colored categories. So how do you consider fed delta itself as a colored category? Well, you say all the arrows that are sent to identities by this map pi are colored arrows. What are the colored arrows in cat? They are just the equivalences of categories. So you say a fair two category is a color preserving functor from fed delta up into cat, such that x0 is discrete. We know what that means. And all the Segal maps, in the sense that I kind of sketched before, are isomorphic. Yeah. So if you think about this, this is formally very, very similar to our simplicial definition of strict two categories. That was a functor from the simplicial delta up into cat, such that x0 is discrete and the Segal maps are isomorphic. But we have this fed delta, we have this color preservation. So what does this describe? Well, I can jump to the result and then I'll try to guide you around that. What Kock proved is that this fair two category is equivalent to the category of bicategories with strict composition law. Well, the fact that you have strict composition law is not really surprising, right? Because all the Segal maps in the structure are isomorphism. So where do you see the weakness? This is not saying that this is strict two categories, bicategories. Well, the weakness is in what is left. And what is it left if you have strict associativity? It's the weak units, the unit laws, right? Well, Cox makes it precise. Again, I have written some slides, but I'm probably not going to have the time to go through all of them. So there is a precise notion of weak units, which looks like this, is an endofunctor together with a right and left constraints satisfying this equation. You can have a category of identity arrows. And a fundamental observation, which, yeah, I think is due to Joachim, and it's a very nice thing, is that the category of identity arrows in a bicategory is equivalent to a discrete category. Yeah. So what Kock does is to say, well, if you have a bicategory, just let me, I've lost track of where I want to go. Okay, so the category of objects, the one that corresponds to x0, is the object of the bicategory C. x1 correspond to the home category. Yes, maybe there is I think there is a slight mistake here, because you have to take all of them, so it would be the coproduct of all these things. And the identity and x of v of 1 corresponds to this category of weak units. Okay. So I also want to maybe make a little further comments about this definition of fair two categories. So we think of x0 as objects, x1 as arrows, and x of v(1) as weak units. But as I said, at this stage, this is only a kind of convention. The Segal maps being isomorphic tells you that we have semi-category structure on U and A with object O, compatible in the sense that this is a semi-functor. But what about this color preservation? This is what I want to discuss. Well, the color preservation is precisely saying that these 5 maps are equivalencies of categories. Why? Because all the arrows that are sent to identity by this pi happens to be generated by just these 5 arrows in fed delta. So it is enough to require this. In particular, look at these 2 maps. This says that this category of weak units is equivalent to the discrete category of objects. Okay. Now here comes the sort of crucial point. We have 2 structures, weakly globular double categories and fair to categories. Both of them have inside them a category which is homotopically discrete. In the case of weakly globular double category is this x0, which encodes what I call the weak globularity condition. In fair to category is the category of weak units. But if you actually look at this very technical proofs of the equivalence of each of these things with bicategories, this proof gives no clue whatsoever as to whether this homotopically discrete structure showing up in both worlds is just a coincidence or there is something kind of deeper behind this. Yeah. And that's the thing that I wanted to understand. And to understand this, you have to try a direct comparison between fair to categories and weakly globular double categories that does not use at all the fact that each of them is suitably equivalent to bicategories. And well, the reason why I was interested in answering this question in dimension 2 is that my interest is to answer this in dimension n for the reason that I will tell you towards the end of the talk. It turns out that just doing this in dimension 2 is far from easy, and it involves a subtle interplay between the simplicial delta and the fed delta. So let me first start from a weakly globular double category and see how can we build a fair to category from it directly without completely ignoring bicategories, okay? So if we go back to this observation of what this definition means, we see that this observation actually amounts to an actual criterion to build a fair to categories. This was already observed by Kock. And the criterion is the following, it's saying, look, you give me a discrete category of objects, a category of arrows, a category of weak units, but we call it like that. These are just 3 categories of which O is discrete. A commuting diagram like this. Then you want to have semi-category structure on U and A with object O, such that these maps are equivalences of categories. If you have this, you have built a fair to categories. So let's start from a weakly globular double category and see whether we can actually get this data. And it turns out that a lot of this is quite straightforward. What is straightforward? The objects are going to be x0d, the discrete category on the connecting point of x0. The arrows are going to be x1. The weak units is going to be x0. And then immediately you have this commuting diagram. What else is straightforward? Remember that x0 was equivalent to x0d, so we know that these 2 maps, which are equal, are equivalencies of categories. We needed that. We also know that these other maps are equivalencies of categories. Why? This comes from this lifting condition in the definition of weakly globular double categories. So bullets 2 and 3 are straightforward. What is left? What is left is that we wanted to have a semi-category structure and on x1 with object x0d, which a priori may sound a bit surprising, right? Because we know that weakly globular double categories mimic a weak structure. So where do you see a strict associativity there? So to explain this, I have to take a step back and tell you a bit more about these weakly globular double categories and some of the techniques that you use to deal with them, which is the notion of Segalic pseudofunctor. Actually, this is a very elementary thing. So you know there is a notion of pseudofunctor from delta up to cat. So if you wrote down the usual diagram we write for Segal maps, because this is a pseudofunctor, this diagram would not commute strictly, right? It would only pseudo-commute. But suppose that in addition, H0 is a discrete category, then this necessarily commutes. So if you have a pseudofunctor where H0 is a discrete category, you can talk about Segal maps. Yeah. So we say that a pseudofunctor from delta up to cat is Segalic if H0 is discrete. So you can talk about Segal map, and then you require all the Segal maps to be isomorphic. Why is this a good thing? For several reasons. So Frank and myself proved, first of all, that there is a pretty straightforward way to associate to a weakly globular double category a Segalic pseudofunctor, which on objects is this. I'm not telling you precisely what is the two-dimensional structure, but it basically comes from these equivalences of categories between this thing and the x1 over x0, etc. This induced Segal map. And we're going to use this in a minute. The second remarkable thing, this is really quite not an obvious fact, but it's crucial in this theory. You know, there is a classical strictification of pseudofunctor into strict functor that you can do in many different ways. But in particular, if you apply the strictification to a Segalic pseudofunctor, you find an actual functor from delta up to cat, which is a weakly globular double category. So weakly globular double category arises as strictification of a particular type of pseudofunctor. Okay, so how can we use this to get out this strictly associative composition? Well, what we want to do is to take this pseudofunctor that we build out of a weakly globular double category and restrict it to the delta mono part. Why do we want to do this? Because remember, we want to try to build semi-categories. But semi-categories are just captured by the delta mono, right? And here is the point. When you do this, you discover that actually what you get is an actual functor from delta mono up into cat. It's not a functor from delta up into cat, but it's a functor from delta mono up. How do you prove it? Well, what is a functor from delta mono up into cat? It's a semi-simplicial object, right? So the phase maps have to be, the phase relations have to be satisfied strictly. Can we prove it? Well, then you have to really look at what is the definition of this map, which I said I didn't give you precisely, but you define this map from the induced Segal maps in their pseudo inverses, and then you prove that this semi-simplicial identities holds, and this is a consequence on the fact that these induced Segal maps are injective on objects. So when you compose with the pseudo inverse, you find the identity. This in itself is a pretty straightforward thing, but somehow it was in front of my nose for many years. And, you know, with Dorette, we were concentrating on another aspect. And then I did a high dimensional case and I just left it there. And when I realized this, immediately I saw the connection with the fair two categories. So to sum up, this is the construction that gives you a functor from weakly globular double categories to fair two categories. At the level of objects, you have x0d, the category of R is x1, and x0 is precisely the category of weak units. Okay. Well, this is just half of the work, but I don't have half of the time, so I'm quite aware of this. So I'm going to skip even further things, but try to give you some intuition for how you go back. So how from a fair two categories, you build a weakly globular double category. Remember that we had a functor from Segalic pseudofunctor into cat2 weakly globular. So what about factoring from fair to categories to Segalic pseudo-functors. That's what exactly one needs to do. The matter is that this can be done. It's very technical because it's quite clear how you want to define this pseudo-functor on objects and on maps and the two-dimensional structure. Proving that it's pseudo-functor takes some work. Okay, so I guess so. Can you tell me how much time exactly I have?
You have about 15 more minutes for the
15 minutes.
Yeah,
okay.
Questions
okay. After. Okay. So basically, this is the point where we need to start digging quite deeply into the properties of the fed delta. Many things were not sort of known when this fed delta was proposed. So I had to work very hard, and I'm still working very hard to figure out all the details. Just to give an idea of what is involved. So if you have a map in delta O, we don't know. So you have a weakly globular double category. So you have a fair to category to start with. So there's nothing you can do with this map alone, right? So what you want to do is to lift this map to a map in fed delta. What does lift means? You take a map that maps to this F through this pi, which maps fed delta into ordinary delta. And then it turns out that each of these can be, so for any object in fed delta, there is an equivalence of categories between this xk and this x eta and x of pi of eta, right? This is not difficult to see because remember that these arrows that are just contracting the lengths, it's this pi have to be sent to equivalences of categories. So you see why we have equivalences of categories here. So what if we take this lift, we pre and post compose with these equivalences of categories, and we define this to be our pseudo-functor on F? Well, there is a little problem with this, right? We have a choice of lift. Could it be that if we choose a different lift, we find a different answer? So one of the big technical points is to make sure that this works for any choice of lift. And you can prove this, but it involves quite a lot of technical things about the fed delta itself. But then it gets even worse because now suppose you have two composable mapping delta O. So what you want to do is to say, okay, let's lift and do what we did before. But we need to lift in a composable way. We know how to lift once, but are we sure that a composable pair of maps lift to a composable pair of maps? Well, it turns out to be the case. So any string of maps in delta can be lifted to a string of maps in fed delta. But the proof of this, again, goes very deeply into properties of the fed delta and how the fed delta and the ordinary delta interact. So this is to say that I think it's not trivial, and I don't think this is surprising because this fed delta is capable of encoding some interesting higher categorical structure. But in the end, this can be done, and so you build this pseudo-functor from fed to categories to Segalic pseudo-functor, and then we just apply what Dorette and myself had worked out, namely the classical strictification returns a weakly globular double categories. So in summary, then in the end, we have this pair of functors, and we show that they are an equivalence of categories after localization with respect to the two equivalences. I kind of didn't tell you in the end the precise definition. I just said there is a fairly straightforward definition of two equivalents on the left-hand side, which mimics by equivalences by categories, and similarly to the right-hand side. So what is involved in proving that this localization gives an equivalence of categories? Well, you have to show that when you go back and forth, right, you find something equivalent to what you started with. And it turns out that this is also not straightforward, because even though the statement of this theorem only involves cat2 weakly globular and FAIR2, to do this proof, at some point you have to slightly enlarge your context and then get back here. Again, I really don't think I have the time to illustrate this, but this is to say that the result itself is non-trivial, and but it does give, in the end, a direct comparison which illustrates that it was not just an accident that you had two homotopically discrete categories hanging around in these two models, because it is precisely the case that this weak globularity condition is about having a category of weak units. Now, as I said, what I really hope, and my interest all along in doing this, is to do this in high dimension. So, no chance to tell you any details in technical details in high dimension, but the big picture is as follows. So, there are several models of weakened categories. In particular, one that uses the simplicial delta is cat and weakly globular. So it's a full subcategory of n4 categories. So you can also think of this as embedded in delta n-1 op cat, where delta n-1 op is the product of n-1 copies of delta op. So this is also what people call a multi-simplicial structure. And I proved it's published in my book, that this is really a model of weakened categories because it is suitably equivalent to the Thompson-Simpson model, and it satisfies the homotopy hypothesis. And you also have these homotopically discrete things at all higher levels in the structure. So then the question is, could we do something similar using fat delta? And, fat delta n-1 op, a kind of multi-fat delta, I don't know what to call it, but you see what I mean. Okay. Well, actually, Joachim Kock proposed such a model. So he has a definition of what he calls fair n categories, which sits inside precisely fat delta n-1 op into cat. And this is a model. Well, I shouldn't say model. This is something that should capture the idea of weakened categories, but where all the compositions are strictly associative and only the units are weak. So you have a kind of minimal type of weakness. However, here is the open question. There is no proof yet that in dimension greater than 3, greater than 2, fair n categories are actually a model of weakened categories. So neither they're being proved to be equivalent to any other model, nor it is known if they satisfy the homotopy hypothesis. When Kock wrote his paper, he conjectured that fair n categories should be a model of weakened categories as a form of what is sometimes called the Simpson weak units conjecture. Simpson conjecture that it should be enough for high category theory to study structures where everything is strictly associative except the unit laws. But the conjecture is still open. So what I conjecture is that fair n is equivalent to cat n weakly globular. I've not proved this, I'm working on this. I'm reasonably hopeful because the techniques that I have used in dimension 2 really have nothing to do with the equivalence of the structure in dimension 2 with bicategories. There's a lot of technical things in my book that I think can be adapted, generalized from the case n equals 2. Not in a straightforward way, because even you can see this also very clearly in the book that I've written. There's a jump in complexity from n equals 2 to n bigger than 2. This is quite often the case in higher category C. My hope is that either me or somebody else sometime in the future will prove this, and this would open, I think, a lot of sort of further insight. I also believe that this approach could be taken for the infinity case, because this Simpson conjecture then would mean that we can really do higher category theory, cutting out a lot of the complexity of higher categories. And I would be delighted if some of you could think of the potential usefulness of such a structure also for kind of more applied perspective, and I would be happy to kind of discuss with you in the future. So a brief summary. Here I have been concentrating mostly on different models of weak two categories, one based on the sort of old-fashioned simplicial delta, and one based on the slightly less known fat delta, which shares some intuition in common with the simplicial delta, like in terms of colored ordinals and in terms of Segal maps, but encodes a much richer structure. The direct comparison between weakly globular double categories and fat two categories illustrates that this new paradigm to weaken categorical structure using the weak globularity condition is really all about the weak units. The proofs, obviously, I didn't have the time to go into the technicalities, but I hope you trust me that some of the proofs are really quite non-trivial, and they involve some subtle properties about this fat delta, which I really think is an interesting category. My real interest in this is that I see a potential for high-dimensional generalization towards, hopefully one day, a proof of the Simpson conjecture. I would also finally like to add something which I forgot to write in the summary. I'm talking to some people in homotopy type theory at the moment, not because I do myself homotopy type theory, but because they are very interested in this fat delta, and some of them are very interested. And the reason is this fat delta is a directed category, you have no non-trivial loops, which is something that people like in homotopy type theory. So this might be also something that could motivate people to take a serious look at this category. And I think that's all. Thanks for your attention.
Thank you so much, Simona. Thank you. Thank you so much for the very intriguing talk and the connections between different things in higher category theory. And I think in the crowd we have a lot of people who are interested in double categories. So I think it's a good time to transition to questions. So how we do this here is that whoever's interested in asking a question, you can raise your hand in the Zoom room, or you can type your question in the meeting chat, and I will ask them on your behalf. So I see that Kevin, you have a question. You can unmute yourself.
I can't hear.
Yeah, we were negotiating. We're in the same room, deciding who to unmute. Thanks for the talk, Simona. I wanted to try to clarify some context of for myself and others here, because I'm only a little bit on top of the recent story with N categories. So I'm aware there's this notion of associative N categories due to Christoph Dorn, which wants to be a notion of weak N category with strict associativity, strict units, and the weakness is all baked into the interchange. So is it the right idea that that associative N categories as well as fair N categories are in a similar position as far as the homotopy hypothesis, that understanding either of their relations to fully weak N categories is open and would resolve Simpson's conjecture?
Yeah, I think it is basically the same, even though the two, I'm vaguely familiar with the work you're referring to. It's a very different type of technology because it's a kind of, well, they call it type theoretic, but it's a kind of operatic technology. So it's a kind of algebraic models of higher categories, whether these are non-algebraic models. Yeah. So attempting to sort of compare them directly gets into this problem that is also something that is not very well understood. I mean, how can you really compare algebraic and non-algebraic definitions? But what you're saying is correct. I mean, you can formulate versions of this Simpson conjecture in various ways, and their formulation is one of them. Yeah.
Thanks. Yeah, that helps.
Thank you. Thank you, Simona. Thank you, Kevin. Are there more questions from the Topos seminar room by any chance? I see a raised hand. Okay. Valeria, you can unmute yourself.
Hi, Simona. I'm very ignorant of all the stuff that you do. So, it's a completely ignoramus question. But I can see that you're putting an awful lot of emphasis on this idea of weak unities, right?
Yeah.
And I wanted to know if you have any kind of intuition that you could give me of why we should be keeping the composition and the associativity kind of strict, but making the units kind of weak. Is there any geometric or whatever things that kind of give you this intuition?
I'm not sure I can really answer this on top of my head. I mean, it is a form of kind of, it is a way to obtain a kind of minimally weak structure. I mean, there's always, I know people that I have even been thinking of doing things the other way around. I mean, I've never thought about this myself, of having strict units and weak associativity. I think Simpson himself, in his original paper where he formulated the conjecture, he might have talked about some intuition coming from topology, but I would have, I mean, I may get back to you if I remember.
No, that's fine. I just kind of thought I was going to try to get some hold on that, but it was a very clear talk. Thank you very much. I kind of I enjoyed it.
Thank you, Valeria. Thank you, Simona. So I think, Kevin, you have a comment. Maybe I can read it out to everyone. So it says as Simpson's paper, which shows it as Kevin, you gave a link to Simpson's paper in the chat, and it says that the paper shows that there's something weird about the three sphere. So perhaps is this in relation to Valeria's question?
Yeah, somehow the need for not fully strict higher categories is all down to the composition of the homotopy groups of the three sphere, at least according to Simpson's paper, just following on from same thing Simona was saying.
Yeah, I think that's my kind of vague memory about that. I mean, am I allowed to ask a question to the audience?
Sure, yes, it's a good idea.
So, because I mean, a lot of you are seriously doing applied category theory, and maybe I have even asked these kind of things in the past, but I have not found an answer, but maybe you guys found an answer. So it would be nice, I think, to see some applied context where this weak globularity condition shows up in a very natural way, if you know what I mean. For example, in topology, in homotopy theory, this is the case. So how did I come to this weak globularity condition? There was a precursor to my work with Pronk. Well, there were really two precursors, but let's talk about the one immediately before that, which is that there was something I did with an algebraic topologist, David Blanc. You take a topological space and you do something to it. Well, you apply the singular functor, you obtain a simplicial set, and then from there you do something, you obtain a bisimplicial set, and then you take the fundamental double groupoid of that, and you obtain a weakly globular double categories where certain things are groupoidal. Yeah. So the kind of groupoidal case of this theory is something that initiated all this, and without having this naturally occurring construction coming from topology, I don't think I would have ever had the confidence to actually do this categorically. I mean, that's at least the way my brain works. And we did this with David in for general N. So in topology, this weakly globular infrastructure arise in a way that you can see very naturally they exist, so to speak. So if somebody asks me about what's an example, well, take a topological space, do this, and you cook up one of these things. I'd love to have an example of even just maybe a weakly globular double category naturally occurring in the context that you guys are interested in applied category theory. So my hope is that you keep in mind this structure, and maybe feel free to contact me and maybe we can discuss something, because I really believe that this is something. It's a new paradigm to weak and categorical structure. It is quite simple in a way, so there may be some applications even behind the kind of world of pure category theory. But I would need your help and intuition for that.
I think that's a really good question, Simona, and I'm not the expert to be able to answer that question, but we do use a lot of double categories in our applied work here at Topos, and maybe there's someone in the Topos seminar room who want to make a comment about that. Evan, Kevin, Owen, anyone, Chris?
I don't really understand exactly what a weakly globular double category is myself, although at least Emily Real claims that there are SIRS epidemiology models that are related. So I'll definitely try to think about it now.
So what is it that Emily says?
She's got or this is probably not Emily. Yeah, this is Emily posting for some adjoint school people in 2021, claiming that there is a weakly globular double category of paths of token placements in Petri nets. I think I haven't read this post, but I think that's what's
I don't think it's Emily. I think so. So I actually that was my team, and yes, we did attempt to answer this question, but we didn't entirely get to an answer from the point of view of applications. And I think that, all of us were more kind of oriented towards the kind of foundational side. But just keep it in mind, and if you think there is something that kind of could ring a bell, then let me know, and then maybe I'll have a thought about it.
That's a good suggestion. Thanks, Simona. So
all right.
We have a question coming from YouTube. So I'll ask on their behalf. So it's from the Vicky Balkan. That's the name of the YouTuber who is asking this question. And the question is, what is the harm objects of a double category? And in other words, what is the base of enrichment for double categories?
Yeah, at the moment, we don't yet have an internal home. We are thinking about it. It would be nice. But I don't know. We don't know yet. So it's not something you can write in a straightforward way, because there is an internal home for double categories, but it doesn't sort of translate in a straightforward way in one for weakly globular double categories. So that's another one of the open questions that I would like very much to understand, and I think Dorette as well. Yeah. So again, if you have any ideas, so both me and Dorette would be delighted to discuss that with you.
Thank you, Simona. So I think I'm going to end the live stream on YouTube, and then we can stay on in the Zoom chat after this for more discussions if people are interested. So let us thank Simona once again. Thank you for the very intriguing talk and really a lot to think about, and thank you for the discussion. I'm going to end the live stream now.
Okay.
Okay. Yeah. So live stream is over.